Welcome back to bilingual e-lectures for diploma students on civil engineering. The subject structural engineering, unit 4, column footings, lecture 4, and these are the worked out examples. And here it is asked to design a square RC footing of uniform thickness, square RC footings, square RC footing of uniform thickness. This is very important, and for a column of size 500 mm by 500 mm carrying a total load of 2500 kilonewton, and the other parameters are given, that is grade of concrete and grade of steel given. Safe bearing capacity of soil is also given for finding out the area of the footing, and step 1 is to find out the size of footing. Load from the column is 2500 kilonewton. Initially we have to assume the self weight of the footing as 10% of column load. So, that comes around 250 kilonewton. So, that the total working load on the soil, and I am saying total working load or total safe load on the soil, characteristic load on the soil is 2750 kilonewton, and the plan area of the footing is found by dividing the total working load on the footing and the SBC of soil. So, plan area is equal to total working load, this is total working load, and this is the safe bearing capacity of soil. So, the area is found to be 11 meter square. Since it is given as a square footing, taking the square root of this area will get the side of the footing. So, 3.31 is the side of the footing, will approximate that to 4 meters. So, the size of the square footing is found to be 4 meters by 4 meters. And the second step is to find the net upward pressure at the base of the footing. So, that is equal to design load. This is the partial safety factor, this is the column load. So, and the net upward pressure, design upward pressure is 234.37 kilonewton per meter square, this is the area of the footing. And bending moment, we know that the bending moment, critical section for the bending moment occurs at this is x1 and I mean x. So, that is at the face of the column. So, this is idealized, or this could be drawn like this also. This is a cantilever with a fixed support, and this is the net upward pressure on the soil W, and we can take this as your L. So, the moment on this area, or the moment due to the load on this hatched area is this, and the projection of the footing from the face of the column for this exercise is found to be 1750 millimeters, and the maximum bending moment at this section is equal to, this is the upward pressure, and this A is nothing but this side, this is A side into distance into 1 is missing, distance into distance by 2. So, this is the intensity of load in terms of area, I mean load in terms of area, kilonewton per meter square, multiplied by this length will give you the load in terms of kilonewton per meter, multiplied by the half of the distance, that is 1.75 by 2. So, that will give you the moment. So, this is the net upward pressure in terms of kilonewton per meter square, and this is the perpendicular length which is to be multiplied to get the UDL, that is kilonewton per meter, and this is the length of this shaded area, and this is the distance of centroid of that load. So, that comes around 1435.52 kilonewton meter. And now, from the bending moment value, equating that bending moment value with the moment of resistance for grade M20 and Fe 415, moment of resistance is equal to 2.76 Bd square, and from this we can get the value of D. So, effective depth from the bending moment consideration is found to be 360.59 millimeter, and to overcome the shear failure it has to be increased by a factor 1.5 to 2. So, in this problem I have taken a factor of 2. So, I have multiplied this by 2. So, 720 mm is the effective depth, and this effective depth is at the reinforcement at the top bar. So, total depth is equal to, or overall depth is equal to, effective depth at the top bar plus half of the diameter plus bottom bar plus cover, and if this is the total depth of the footing. See, from this to the center of reinforcement, this is effective depth what we have calculated, and from this to this half the diameter, and this is the full diameter. This is dia by 2 and this is the full diameter, and this is the cover. So, total depth or overall depth of the footing D, this D is equal to, this is 720 mm plus the diameter here assumed is 25 mm bar. So, dia by 2 is, this is dia by 2 plus this is D plus dia by 2 plus D plus cover. So, this will give you the total thickness of the footing, and now it is found to be 810 millimeters. And from the bending moment consideration, we have to find out the area of steel for the footing. So, the area of steel is found by using this expression 0.87 FIAST into D minus FIAST by FCK into B. So, substituting the relevant values, it will be of quadratic equation. Solving the quadratic equation, AST is found to be 6890 millimeter square, and this area of steel is to be checked for the minimum area of steel that is to be provided for the footing. Since it is similar to that of a slab, the minimum area of steel for a slab is 0.12% of the gross area if you use Fe 415 and other HYSD bars. So, by using the same expression, the minimum area of steel 0.12% of gross area, this is 0.12%, and this is the gross area of footing, this is AG of the footing, and it comes around 3888 millimeter square. This is the minimum area to be provided, whereas as per the design we got this as 6890 millimeter square. Since this is less than that, whatever the design area of steel, we have to provide the design area of steel, and that comes around 16 numbers of 25 mm bars. Either you can calculate the spacing or you can calculate the number of bars. So, here I have calculated the number of bars, it comes around 16 numbers. So, the actual area of steel here provided is 7850 millimeter square in each direction. Since it is a square footing, I have calculated, or here it is calculated in only one direction, and the same reinforcement with same diameter and spacing will be used in the other direction also. And the check for the development length LD, this is of course phi into sigma s divided by 4 times of tau BD, where phi is the diameter of the bar and sigma s here is 0.87 Fy sorry, and tau BD is the design bond stress as per the table given design. So, now substituting the relevant values, this is the diameter of the bar and this is 0.87 Fy is sigma s divided by 4 times of tau BD. Tau BD for M20 grade of concrete is 1.2 only, and we have to increase it by 60%. So, that this is 1.6 comes into the picture. So, the development length of 25 mm dia bar is found to be 1175 mm, whereas the projected length of the column footing is 1750 mm. Therefore, it has got sufficient development length, that is the main reinforcement or the longitudinal reinforcement of the footing has got the sufficient length. So, this is the cross section of footing which describes the size of footing as 4000 by 4000 and the overall depth as 810 mm, and the main reinforcement in the footing is 16 numbers of 25 mm dia bars in both the directions, and this is of course the uniform thickness footing. This is a column of size this, and up to this a question will be asked for 10 marks, and the check for bearing stress, check for safe bearing capacity of soil, check for one way shear and check for two way shear, that comes for other 10 marks problem. And here the second type of problem is illustrated. A RC concrete footing has to transfer a dead load of 900 and imposed load 400 from a square column, and safe bearing capacity is given. Design the footing with uniform thickness, this is very important of course, and check the footing for one way shear, punching shear, bearing stress and safe bearing capacity of soil. This forms the second type of problem, which is also carrying 10 marks. Now, the data given are written here, and size of the footing from the expression total load on footing divided by SPC of soil. So, that comes around 7.15 meter square. Since it is a square footing, take the square root to get the side of the footing. So, side of the footing is 2.8 meter by 2.8 meter, and net upward from the design load, this is found to be 248.72 kilonewton per meter square, and bending moment along this critical section XX, and the projected length for this exercise is found to be 1200 millimeters, and the bending moment along this direction XX is equal to 501.14 kilonewton meter. And to get the depth, we have to equate this bending moment to the moment of resistance value. So, by equating that, depth, effective depth of the footing is found to be 254.65 millimeters. And again we have to have a factor to overcome the shear failure. This effective depth, whatever that we got from the bending moment, is to be multiplied by a factor ranging from 1.5 to 2. So, here it is taken as 2. So, and it is rounded off. Here it is provided the effective depth as 500 mm for the top layers, and assuming the cover as 50 mm and the 20 mm diameter bars, the overall thickness of the footing is found to be 580 millimeters. Tension reinforcement, equating the bending moment to the equation 0.87 Fy ast into d minus Fy ast by Fck into b. On solving the quadratic equation, area of steel is found to be 2900 millimeter square. Check for the minimum area of steel and provide the number of bars. Here it is 10 numbers of 20 mm dia bars, and the actual area of steel is found to be 3140 millimeter square in both the directions, and the percentage of area of steel is 0.22. Again the development length phi into sigma s divided by 4 tau BD. Required development length is 940 mm. Projection of footing from the face of the column is 1200 mm, and therefore, the development length is also okay. And here comes the check for transverse shear, and the critical section for transverse shear lies at a distance of d from the face of column. So, from this sketch, this is the face of column and this is a distance d. So, now y shows the critical section for shear, and that means whatever be the shear force coming in the hatched area or generated in the hatched area should be resisted by the area across this y line. Now, length of footing beyond the critical section y is equal to 700 mm, and the transverse shear across section y that is equal to, this is the net upward pressure on the soil for this footing 248.72 into the area 2800 here, and this is 7000. So, this in terms of meters. So, 2800 and 700 mm, and the total shear on the hatched area is found to be 487.49 kilonewton. And now, the nominal shear stress across the section y, this is the shear force divided by the area. So, area is this. Now, the shear stress in the hatched area is found to be 0.34 Newton per millimeter square, and permissible shear stress in the concrete of for the percentage of steel 0.22 from the table 19 of IS 456 2000 is found to be 0.336 Newton per millimeter square, and the actual shear stress is 0.34 Newton per millimeter square, and the permissible shear stress is 0.336 Newton per millimeter square. Hence, the footing is safe in one way shear, since that is this is 0.34 and it is almost 0.34. So, which is equal. So, the footing is safe in one way shear. And the other check for the shear is punching or two way shear. Critical section for two way shear occurs at a distance of d by 2 from the face of column. So, this distance is d by 2. So, this is from the face of the column on all the four sides. So, section Z shows the critical section for punching shear, and side of the shear section is this column width is 400, on either side is 250. So, 250 plus 250 plus 400, that will give you 900 mm. So, one side of the shear section is 900, on all the four sides it is equal. So, 900 and punching shear across the section ZZ is equal to intensity of the pressure, this is W, net upward pressure W, into the hatched area. So, hatched area means this total area minus this area. So, total area is 2.8, outer area minus inner area, I can say 2.8 into 2.8 is outer area and 0.9 by 0.9 is the inner area. So, hatched area is equal to this minus this, and this area into the intensity will give you the total shear on the hatched area, and that shear is to be resisted by the concrete on the along the across the section ZZ. So, this is the shear force and this is the area and this is the shear stress. So, this is the shear force and this is the area. So, force by area will give you the stress, and that shear stress is found to be 0.971 Newton per millimeter square, and this is to be checked with the maximum permitted value by the code. So, maximum value of shear stress in concrete is Ks into tau c, and Ks is equal to, since it is a square column, Ks is equal to 1. So, tau c z is equal to 0.25 times of root of FCK, and this value is found to be 1.118 Newton per millimeter square. Since tau v z is less than this value, the footing is safe in punching shear also. And check for bearing stress. So, this area, this is A1 area, and here this is A2 area. Now, side of frustum of pyramid at the base, of course, this is the overall depth, and this slope is, if this is 1, this is 2. So, of course, the sketch is not appropriate, and of course, it is not drawn with dimensions, and the slope is 1, this is 2. So, 580 multiplied by 2 will give you 1160, this is 2 times of 580. So, this is 1160, again 1160 on this side, and width of the column is added to get the width of the frustum at the base, frustum of pyramid at the base. So, that is equal to 2720 mm. Now, supporting area for bearing of footing is equal, since this is a square one, 2.72 meters by 2.72 meters is this area and the base area, and loaded area of the column and the base here. So, this is 0.4 meters by 0.4 meters, it is 0.16 meter square, and the value square root of A1 by A2, that is found to be 6.8, but the restricted to 2, that is very important to note, do not put the same value as 6.8, and this is restricted to 2 means instead of 6.8 you have to substitute 2 only. So, permissible bearing stress is found to be 0.45 FCK square root of A1 by A2, where this is 0.45 FCK, and this value, though we have got the value as 6.8, which is restricted to 2, this you have to remember. Now, the permissible bearing stress is found to be 18 Newton per millimeter square, but the actual bearing stress on the loaded area, this is the load and this is the area, this is the area and this is the load. Now, so load by area is this stress, and the bearing stress, permissible bearing stress is 18 Newton per millimeter square, whereas the actual stress is 12.18 millimeter square Newton per millimeter square. Since actual bearing stress is less than the permissible bearing stress, the footing is safe in bearing stress or bearing pressure also. And the last check is to check the safe bearing capacity of soil. So, load on soil is here, self weight of the footing is calculated, total load on the soil, pressure on the soil is load by area, that gives you 180.32 kilonewton per meter square, and which is less than the safe bearing capacity of the soil given in the problem, and therefore, soil will not fail. So, this footing is also safe in safe bearing capacity. Hence, all the checks are over. I will repeat the checks. So, first check is development length. For that, find the development length by using this expression. Check or find the projected length from the face of the column. If the development length is within the projected length of the column, then the development length check is over. Okay. And check for one way shear, calculate the shear in the hatched area and calculate the shear stress. Check the shear stress for this permissible shear stress, and if the actual shear stress or nominal shear stress is less than the permissible shear stress as per table 19, then the footing is safe in one way shear. In two way shear, the critical section lies at a distance of d by 2 from the face of the column, and find the shear stress across the section ZZ and check that nominal shear stress to that of the permissible stress given by the code, that is Ks into tau c. If the nominal shear stress across the critical section ZZZ is less than the permissible shear stress in concrete Ks tau c Z, then the footing is safe in punching shear also. And the third check is check for bearing stress. Again, if calculate the actual bearing stress by using this expression, actual bearing stress is load divided by the area on the column at the base. So, this is actual stress, and the permissible stress is 0.45 FCK into root of A1 by A2, where A1 is the area of the frustum of pyramid at the base and A2 is the area of column at the bottom. So, if actual bearing stress on the loaded area is less than the permissible bearing stress, then the footing is safe in bearing stress also or bearing pressure also. And the last check, safe bearing capacity of soil. Add the self weight of the footing and find the total load on the soil, calculate the pressure on the soil. If this pressure is less than the safe bearing capacity of the soil, then the soil will not fail, hence the footing is safe. So, this is how we have to perform the check for the RC column footing. So, the answer for this exercise is size of the footing, thickness of the footing and the area of steel, and also we can add all the checks are performed. And this is an example for a square column of size 350 mm which carries a sloped square footing. So far in exercise 1 and 2 we have seen only the uniformed thickness footing, and in general or in practice we used to put only sloped footing, maybe of a square or maybe of a rectangle or maybe of circle, we will be using only sloped footing, and we will see this example. So, column size, axial load, safe bearing capacity of soil and the grade, we are asked to design the footing. Again the design means we have to give the plan size of the footing, total depth of the footing, area of steel in both the directions, in shorter direction as well as in longer direction in terms of diameter of the bar and number of bars. So, now this is the size of load on the column, add 10% total load on soil, get the area of footing, take the square root, get the side of the footing. So, the side of the footing, square footing is found to be 2.8 meter by 2.8 meter for this exercise, and net upward pressure is the design load on the soil by area of footing, that is equal to 137.93 kilonewton per meter square. It is not millimeter square, it is meter square. I am sorry. Kilonewton per meter square, this is to be corrected. and again bending moment at the critical section face of the column. So, the projected length is found to be 1225 millimeters, bending moment along this section x x, and this is the length of the cantilever portion, and we can take this as the fixed support. We can take a diagram like this, and this is the loading W, and this is the L or projected length. Now, the bending moment along this section x x is found to be 236.55 kilonewton per meter, and I think this is 137.93 is the W, and this is 2.8 is okay. This is the A direction or A1, and 1.225 I think W L square by 2, this is to be squared here, L square by 2, right. So, the value comes as 236.55 kilonewton meter, and depth of the footing required, and for the sloped footing the effective breadth in x1 direction, of course, we have to arrive at this value. So, from the general design procedure, this is equal to A plus A minus A by 6, where A is the this length, that is column dimension, and this is again this is A. So, 1/6 of this difference. So, that is equal to 750 mm, and this is effective breadth, this is actually 750 mm, this is 750, and effective depth required is from the bending moment consideration or equating bending moment to MR. So, bending moment is from the previous slide 236.55 kilonewton meter is the bending moment. Equating that bending moment to the moment of resistance 2.98 BD square for the given grade of concrete and steel, we get depth, effective depth, this is whole square root, is equal to 325.33 millimeters, and again it is to be increased to overcome the shear failure. So, it is to be multiplied by a factor 1.5 to 2. So, that comes around 475 mm. Adopting the cover and other diameter of bars, the total depth of the footing at the face of the column at this point which is found to be, or which is, this is equal to 550 mm, and at the edge this is 200 mm. Tension reinforcement, by substituting the bending moment value in this equation, solving the quadratic equation, AST is found to be this much, and providing 13 numbers of 16 mm dia bars, AST provided is this much, that is percentage of steel is 0.773%. And again check for one way shear, transverse shear in the shaded area, this is W and this is 2.8 meters is this length, and probably this is the hatched portion. In the hatched portion, the shear is found to be 289.65 kilonewton, this is the intensity, and probably this is your A value, and this is 1225, and this distance is D, this is not correct, this is 475. So, from this point to this point. So, now this is the 1225 minus 475, that is 1225 minus 475 will give you this width and this length 2.8, and this is the intensity, and of course, this is the hatched portion. Length of the hatched portion is 2800 and breadth of the hatched portion is 1225 minus 475. So, this is the breadth of the hatched portion, this is the length of the hatched portion, and this gives you the area of the hatched portion. These two parameters will give you the area of the hatched portion, and this is the intensity of soil pressure. So, this will give you the transverse shear. So, this is the intensity and this is the area that will give you the shear force on the hatched portion of the footing. Now, the total depth of the footing at the middle of the section, because the section goes like this at shear at here edge thickness is 200, whereas at this point the edge thickness is 550 mm. So, there is a slope from this point to this point. So, the slope starts at 200 mm above the bottom point of this footing at this point and goes like this and joins at this point. Now, so the cross section is shown here. So, up to this entire area will be having a flat footing, and above that 200 mm depth there will be a slope from this point to this point. The difference in depth between this and this is 550 minus 200. So, 350 mm is the slope difference. Now, total depth of the footing at the middle of the section from the geometry is found to be 200. This is the flat 200 plus this depth. So, this depth is not again 200, this is to be corrected here, this is not 200. So, this is calculated like this, 550 minus 200 for 750 mm for 1225 mm for 750 mm. So, total depth of the footing at the middle of the section is found to be 414.28 millimeters, and accordingly the effective depth at the center is found, effective depth at the edges are found, breadth of the section at the top, and now effective area resisting the transverse shear, flat area as well as the sloping area, this is found to be this much, and the nominal shear stress, of course, this is load by area, is found to be 0.369 Newton per millimeter square, and the design strength of the concrete for the percentage of area of steel 0.773 is 0.56. Since the nominal shear stress is less than the design shear stress, the footing is safe in one way shear. Similarly, the footing is to be checked for punching shear, and in the sketch Z shows the critical section for punching shear, and the punching shear stress or nominal shear stress across the section Z is found to be 0.73 Newton per millimeter square. Permissible shear stress is found to be 1.11. Since the nominal shear stress 0.73 is less than the permissible shear stress, the footing is safe in two-way shear also. So, the answer is size of the footing, thickness of the footing means overall thickness of the footing at the face of the column, and overall thickness of the footing at the edge, and the reinforcement of the footing in both the directions, 13 numbers of 16 mm dia bars in each. So, we have seen in this chapter design of RC column footings of square shape with uniform thickness, and a rectangular column footing with uniform thickness, and a sloped footing of square shape, and the steps involved in the design of column footings, and the results, the output that you have to give for the design of column footings. I hope this presentation have touched the important sums or problems for the diploma level students on design of column footings and its checks. Thank you.